Welcome to SanfordFlipMath. This is AP Calculus. We are continuing to work from the Finney, Demana, Waits, Kennedy book, 3rd edition. And we are in the beginning of Chapter 5 still. And we've been estimating area with rectangular approximation methods. And we are going to kind of ease into finding area in a little more precise manner. And so this next section is about definite integrals, whatever those are. Okay, so definite integrals. And I really don't know the history of that word integral being used in this context, but I will tell you that it is going to all be about area. Okay, so that's where we're going. And what we've kind of already done is this, and this looks a little scary, but just a reminder that this sigma is a Greek letter. It's like the letter S, and sigma, like S, in this case represents sum. In other words, add them up. Okay, and so this is what we've been doing, is we've been adding up areas, and all this is saying is add up all the areas from the first area to the nth area, the last area. And as you're adding up all of those areas, once you add it all up, you'll have a total. Okay, and if they are rectangles, then this would be like the height, and that delta x would be the base, so base times height would be the area of a rectangle. And the idea is that this is an x value somewhere in that little rectangle, and so it could be a left end, it could be a right end, could be a mid, you know, if we're doing left, right, or mid ram, or it could even be a different x value. It doesn't have to be those are just the standard ones that we tend to look at. And then you multiply it by the base, and so that height times base is the area of that rectangle, and again you would add them up. And the implication here is if we were talking about between a left endpoint and a right endpoint, then we would subtract those x values. Okay, so that would be our change in x for the whole thing. And each one, then if we had 5 rectangles, we'd divide by 5 or something like that. Okay. Now, the idea is, okay, so just to get a little picture of what's going on, just a quick little idea. Okay, again, if we were talking about, you know, making rectangles, you know, like if this is left ram, you know, something like this. Okay, just to get a feel for what's going on. And I think we've talked a little bit about the fact that if we used more rectangles, then we would get a better approximation. Okay, so in other words, there wouldn't be so much error because we'd have a bunch of rectangles and they would be closer to the curve. Each time we do a rectangle, it's closer to the curve. Okay, and we could get even closer than that. Okay, and I'm not going to draw 100,000 of these. I know some of you are freaking out going, look, this video is already going to be long enough. Sorry. Okay, so here's the idea. If we keep getting more and more and more rectangles, then we actually end up getting closer and closer to the actual area. Okay, so that's what this is saying. This is saying if the number of rectangles gets huge, then the idea is this thing becomes this. And this is what's called an integral. Okay, and what I need you to know right now is this represents area. Okay, so here's the picture that goes with this. Okay, so I have some lovely graph of, let's do y equals f, and it looks like a g, sorry, I changed from an f to a y in mid letter. Okay, so y equals f of x, and we'll draw this from A to B, and this area from A to B of f of x dx. Now let's talk about how this kind of fits together. Okay, I just need to not be distracted by a bunch of stuff. Okay. All right, so here we go. This A and this B are the same A and B that goes with this, and so this is the left end, this is the right end, this is the Y value, this represents the Y value, and then this thing represents the delta x, and we know that from when we were talking about like dy dx, and we might multiply by dx the change in x to get the dy. Same idea. It's just we're talking about in this setting. So again, this is like the base, this is like the height in terms of notation. Okay? All right, so again, what does this represent? This is the left or lower limit of integration. So this is the right or upper limit of integration. Okay. This is what's referred to as the integrand. This is the function that we are doing the integral of. Okay. We are doing the integral with respect to x, and the idea here is it's kind of like when we do derivative, we do it with respect to x or some variable. And this thing, so the whole idea is this is based on a bunch of rectangles. Well, this symbol really comes from taking an s and stretching it. So it's a fancy s. So it comes from the idea of sum, much like the sigma. It's just kind of a special one, kind of, you know, fancied up a little bit. Okay? And if you have an f of x, a function that is non-negative during that, over that interval, then what you end up finding is area. Okay, so just understand that this symbol itself, this expression itself, could give you a positive or negative or even zero answer, and it's based on base times height. And if we're talking about things that are underneath the x-axis, then you could have a value that's negative. Okay, it's and if you do the absolute value of all of that stuff, then it becomes what we normally think of as area in normal square units. Okay, all right. Well, let's kind of play around with some of this. Okay. Okay, so we're going to do the integral from 1 to 3 of 7 dx. So remember that this thing in here, the integrand, the argument for the integral, is the f of x. So we're saying f of x is 7, or in other words, y equals 7. Well, let's just kind of remind ourselves what that looks like. Okay, so, okay, and it's going to be a very exciting graph. And yep, there it is. Okay, and this particular graph, we are interested in looking at it from 1 to 3. Okay, so really what this is asking me for is this is above the x-axis, and so it is asking me for this area. Isn't that exciting? So here we go. I know this is going to be very high tech. This area, so 3 minus 1 is 2. This height is 7. Ooh, yeah, it would help if you actually write the number that you say. 7. And then altogether then, 2 times 7 is 14. So the answer to this is 14. I mean, really that is it. Now, obviously it's going to get harder than this, but right now we're focusing on what is the meaning of this notation. Okay? So right now, the meaning of this notation is, what's the area? Okay. Okay. let's go from -2 to 4, and let's do 1 dx. This is very exciting. Okay, again, this is the y. This is f of x equals 1. This is the argument of the integral. Okay, so we're going to do just a little graph so we understand what's going on here. Okay, and we're going to graph y equals 1. Okay, and I need to look at this from -2 all the way to 4. 1, 2, 3, 4. Okay, so that area is going to be 6 times 1, which is 6. So the value for this integral is 6. Okay. All right, well, let's do something just a little bit more interesting. Let's not get crazy or anything. Let's go from -1 to 3, and let's do x plus 1 dx. Okay. All right, so again, this is the integrand. So this is f of x. Okay. And so now we're going to do a little graph like we have been doing. It's just instead of it being a horizontal line, it'll be a little more interesting. Okay. Okay, so from, let's do 1, 2, something like that. Okay, so it has a y-intercept of 1, it's got a slope of 1, and it's going to look something like this. Okay, and we want the area then from -1 all the way to 3. So this is the area that we're actually interested in. Okay, now, I guess it's worth noting, I guess it's kind of obvious here, but just so in case it wasn't, this is a triangle now. So to do this integral, I'm going to do the area equals 1/2 base times height. Well, 1/2, well, the base of this thing happens to be 1, 2, 3, 4. Well, and the height, well, it kind of depends on what the y value is up here. So this is at the order pair 3, comma, well, if I do 3 plus 1, that's 4, so 3, 4. So it looks like the height is also 4. So half of 4 is 2, 2 times 4 is 8. Okay. So conceptually what we're talking about is area. Okay. All right, so let's evaluate another one that is fairly straightforward but with a little twist. I knew you'd be excited about the twist. Okay. So let's do the integral of, what was it, x plus 1? Sorry. Yeah, okay, I'll do it again. X plus 1. And let's do from -3 to -1. Okay. All right, so again, I'm going to redraw it just so I don't have to worry about figuring out all of the different kind of shadings and things like that from the last one. Okay, so 1, and again my slope, I want this in red to follow my pattern. So again, this is y equals x plus 1. Okay, so it looks something like this. Okay, now the twist here is that I'm starting at -3 and I'm going to 1. So the area I'm looking at is actually on the left. Okay, sorry, my little shading is spilling out because I didn't get a very fine drawing tool. Okay, all right, so here's the twist. Again, I'm still going to do area as 1/2 base times height because it's a triangle. And the basic concept here is that this width, this base is 2. And this height, well, again, I can get a y value to go with this. So this is -3 comma, well, -3 plus 1 is -2. So the height of this thing is -2. That -2 stands. It's going to stay just like that. Okay. So half of 2 is 1. So the value for this integral is -2. The value for this definite integral is -2. So Okay, quick little note to self. If we're talking about below the x-axis, the integral is negative. Now, we have to be really careful about wording here, and I'm trying to be careful too because I can mess this up, okay? Technically, the area between -3 and -1 is 2, because we think of area as a positive number. The value for the integral, however, is -2. Okay, so we have to kind of be careful. Sometimes I try and emphasize the wording, you know, if I ask for total area or specific area or, you know, something like that, if I'm making it real clear that I'm not talking about just the integral's value, then it has to be positive. Okay, so that's kind of a big deal. So if we're talking about below the x-axis, then the integral is negative. If we're talking about the keyword area or total area, that word implies that we have to be positive. Okay, so that's kind of a big deal. It's a detail thing that's easy to mess up. All right, so with that in mind, let's do this. Let's do the integral from -3 to +3 of x plus 1. Okay, quick little note to self here. This little guy must be here. Even if we don't really do anything with it, it is part of the notation. It's part of this idea that it came from a bunch of rectangles, and the delta x, the width of that rectangle, corresponds to the dx. Okay, delta x and dx are kind of like analogous to each other. Okay, all right, so let me get rid of that. Okay, all right, so back to the graph. It's one of those things that people forget about writing. All right, here we go. So again, I'm going to graph this bad boy. What you going to do? In red, and we're going up 1, etc. Okay, and now I want the area from, I want the integral, see, I got to be careful with my wording, from -3 to +3. Okay, and just a reminder, this was at 3, 4, and this little guy was at -3, -2. Okay, so here's the thing. If I'm going to do this by looking at areas, and that's what I'm doing, okay, then I need to look at this area. Okay, so remember, this little area of a triangle, 1/2 base times height, this thing was 8. We did that before. This little guy right here, area of this triangle, was 1/2 times 2 times -2, so that was -2. Okay, that's for this one. Okay, so when I do this integral, it's actually going to be -2, yes, -2, plus 8. Sorry, lots of clunking because I'm trying to color coordinate a little bit here. Okay, so the value for that integral is 6. Excuse me. Okay, now let me do a little contrast then. If I asked for the area between -3 and 3, then I would take that -2 and I would make it positive, plus that 8, which was already positive, make it positive or not, I don't care, and that's 10. Okay, which is normally what we would think of more intuitively. Okay, so if I was asking for area over that interval, it's 10. If I was asking for the value of the integral, it's 6. Kind of a detail thing, but it's got to happen that way. Okay, we're just going to do one more, and I think you have a rough idea of what's going on. I just want to do one more. Okay, so let's go from -2 to 5, and let's do 3x plus 1. I don't know what the deal is with my plus 1s today. Oh, I should have done it a little bit different, but that's all right. Okay, so now sometimes the graph is going to get a little more out of control, so maybe I shouldn't have, because I'm going to have to go up to 16. That's not going to happen. All right, so let's skip the scale on this, and we'll just remember that it's going to cross at 1, and it's going to look something like that. So I'm just eyeballing. Okay. All right, so we're talking from -2. Oh, I messed up my color. All right, so from -2 all the way to +5, 1, 2, 3, 4, 5. It's going to look something like that. I really need to know this value here because I need to know what to do with it. I'm not sure, you know, if I have it too steep, not steep enough. It's probably not steep enough, but I want to kind of at least get -2, and then 3 times -2 would be -6, plus 1 would be -5. All right, so probably should really do something more like this. All right, so I'm going to just adjust that, and I'm going to do, we'll do our best to ignore this line. I don't know if I can get rid of it or if it'll get rid of too much. We'll try it. Oh, that was awesome. Perfect. All right, so this is going to go up to here, and this is at 3, 5. Okay? All right, so part of the issue here for us is we're going to have to figure out what this point is, because I can't do this area by hand until I know what that x value is. So I really have to do a little bit of algebra here for a second. So 3x plus 1 equals 0. X is going to be -1/3. So this entire length is going to be 1, 2, 3, 4, 5, and 1/3, which I absolutely hate. So I'm going to call it 16/3. So 1/2 times a base of 16/3 times a height of 5. Okay, so this is going to be 80/6. No, I can do a little reducing here. So that's 8. So about 40/3. Okay. Okay, on the other end, okay, so again, we're going from -2. The point where this crosses was at -1/3. So this is going to be, that distance is going to be 1 2/3. Okay, so from -2 to -1/3 is 1 2/3, so that's 5/3. So the area for that little piece is going to be 1/2 times 5/3 times -5, again negative. So this is going to be -25/6. I should have just left that 6. All right, so here we go. Let's put all this together because I know you got stuff to do, and so do I. Okay, so the integral of f of x dx from -2 to 5, I believe it was, is going to be equal to -25/6 plus, I'm sorry, I'm going to switch this right now to 80/6. Okay, so this is 55/6. Okay, now quick little note, and part of the problem was I was just doing this on the fly, but keep in mind that we've done a fair amount here with rectangles and triangles. You can be doing integrals. Also, you know, if I have some line like this, maybe I'm going to do an integral from here to here. Well, that's really a trapezoid, and so just a quick little reminder for those of you watching at home. That's the formula for the area of a trapezoid, but remember base 1 and base 2 are the parallel sides, and the height is the distance between them. Okay, so if that comes up, now you're certainly welcome to do something like, you could find the area of a whole triangle, and then if you wanted to subtract off a triangle, or some of you maybe would prefer to find the area of a rectangle and then add on the area of a triangle. Well, you can do that too. All right, so there are a lot of ways to handle this, and I need to be done. So thanks for watching. This is just getting us started with integrals. It is about what they are about, and this is kind of like when we learned slope at the beginning for derivative. This is how we get started. Okay. All right, thanks for watching. Sanford Flip Math. I guess we are out of here.